Hello students, welcome back to next session. In this, we are going to see problems on Bell-Coleman cycle. These are the topics we have covered. In next session, we are going to complete refrigerants, desirable properties, classification, and its nomenclature. So, first problem, in a refrigeration plant, working on the Bell-Coleman cycle, air is compressed to 5 bar from 1 bar. Its initial temperature is 10 degrees Celsius. After compression, the air is cooled up to 20 degrees Celsius in a cooler before expanding back to a pressure of 1 bar. So in this, we have to determine two parameters. One is theoretical COP of the plant, the net refrigerating effect. So given data is P2 equal to P3, that is 5 bar. So that is 5 bar is given here. That is bulk air is compressed to 5 bar from 1 bar. So P1 is equal to P4, that is 1 bar, and this will be clear here. So P1 and P4 equal to 1 bar, and P2 and P3 is equal to 5 bar. T1 equal to 10 degrees Celsius, so that is 283 Kelvin. T3 equal to 20 degrees Celsius, that is equal to 293 degree Kelvin. And Cp and Cv, specific heats also given, 1.005, and Cv is 0.718 kilojoules per kg Kelvin. So here these are the data available, and with respect to this, and we have 283 is the T1, and T2 is unknown, T4 is unknown, and we have 283 is T3. So these are the data available. With this, we have to calculate COP, theoretical COP, as well as net refrigerating effect. Second problem, a refrigerator working on the Bell-Coleman cycle operates between pressures of 1.05 bar and 8.5 bar. Air is drawn from the cold chamber at 10 degrees Celsius, compressed and then cooled to 30 degrees Celsius before entering the expansion cylinder. The expansion and compression follow the law PV to the power 1.3 equal to constant. So gamma is equal to 1.3. Determine the theoretical COP of the system. So the given data are P1 equal to P4, that is 1.05, P2 equal to P3, that is 8.5 bar, T1 equal to 10 degrees Celsius equal to 283 degree Kelvin, and T3 equal to 30 degrees Celsius, that is equal to 303 Kelvin. So polytropic index, that is n equal to 1.3 given. So PV power n 1.3 equal to constant. So that is 1.3 given in the problem. And it's a PV diagram. We have PV power 1.3 equal to C, and this is the TS diagram. So here T1 equal to 283 and T3 equal to 303 degree Kelvin. So these are the data available. With this, we can easily calculate the theoretical COP of the system. So with that available data, we can calculate isentropic relations for compression and expansion. Since the compression and expansion follow the law PV power n equal to C, we can have this. For isentropic compression process 1 to 2, T2 divided by T1 equal to P2 divided by P1 to the power n minus 1 divided by n. So that is equal to 8.5 divided by 1.05 to the power 1.3 minus 1 divided by 1.3. So that becomes 1.62. So T2 equal to T1 into 1.62. So that is 458.5 degree Kelvin. So T2 we have found out here. For isentropic expansion process, that is 3 to 4, T3 divided by T4, P3 divided by P4 to the power n minus 1 divided by n. So that becomes 1.62. So the ratio of T3 by T4 is 1.62. So from here we can find out this T4. So T3 divided by 1.62. So that is T3, we know it is 303 degree Kelvin divided by 1.62 equal to 187 degree Kelvin. And calculation of the COP, and we need to calculate the theoretical COP. The compression or expansion ratio is given by Rp equal to P2 by P1 equal to P3 by P4, that is equal to 8.5 divided by 1.05, that is equal to 5. So Rp we have calculated here. So with that COP of the plant, the whole plant is calculated like this. COP equal to, in terms of T4 divided by T3 minus T4 equal to 187 divided by 303 minus 187 equal to 1.712. So this is the first answer. And second answer, theoretical coefficient can be calculated like this. It is in terms of n and gamma, n divided by n minus 1 into gamma minus 1 divided by gamma into T1 minus T4 divided by T2 minus T3 minus T1 minus T4. So this is theoretical COP relation. Substituting all the values here, we are getting the COP, theoretical COP as 1.3. So this is the answer for this. And final answer is 1.3 is the theoretical COP for this refrigeration system. So coming to next problem, that is problem number 3, example 3. The atmospheric air at pressure 1 bar and temperature minus 5 degrees Celsius is drawn into the cylinder of the compressor of a Bell-Coleman refrigeration system. It is compressed isentropically to a pressure of 5 bar in the cooler. The compressed air is cooled to 15 degrees Celsius with the pressure remaining the same. It is then expanded to pressure of 1 bar in an expansion cylinder, from where it is passed to the cold chamber, and we need to find the work done per kg of air and the COP of the plant. The given data is P1 equal to P4 that is equal to 1 bar, P2 equal to P3 that is equal to 5 bar, T1 equal to 268 degree that is minus 5 degrees Celsius, T3 equal to 15 degrees Celsius that is equal to 280 degree Kelvin, and the polytropic index and specific heats the N equal to 1.2, gamma equal to 1.4, Cp equal to 1 kilojoules per kg Kelvin. And this is the PV and the TS diagrams, and you can see here this is T1 that is 260H and T3 that is 280H. So these two are known temperatures, and T2 and T4 are unknown that we need to find here. So polytropic expansion, that is PV equal to 1 point PV power on 0.4 equal to C, and PV power 1.2 equal to C for polytropic compression, expansion, and this is polytropic expansion. So work done per kg of air, let T2 and T3 be the temperatures at the end of the compression and expansion respectively. The compression process 1 to 2 is isentropic and follows the law PV 1.4 equal to constant. Thus, we use the isentropic relation T2 by T1 equal to P2 by P1, gamma minus 1 by gamma equal to 5 by 1, 1.4 minus 1 divided by 1.4, that is equal to 1.585, and T2 can be find out here, that is 424.8 degree Kelvin. So now only T1 is unknown. So this T1 can be calculated like this. So PV power 1.2 equal to a constant. So T3 by T4, P3 by P4, n minus 1 by n, 5 by 1, 1.2 minus 1 divided by 1.2. So that is 1.13. So T4 is equal to T3 by 1.31. So that is 220 degree Kelvin. So that is T4, and we know now T1, T2, T3 as well as T4. So work done per kg of air. So WC equal to work done from 1 to 2 process. So gamma divided by gamma minus 1 into R into T2 minus T1. WC equal to, now we have to substitute these values, and once we substitute the values, we are getting work done during compression is 159 kilojoules per kg, and taking R equal to 0.287 kilojoules per kg degree Kelvin. So this is the value we are considering for R. So work done by the expander, that is process 3 to 4. So W3 to 4 equal to WE in terms of N divided by N minus 1 into R, T3 minus T4. Now the R is calculated or considered 0.287 kilojoules per degree Kelvin, and 1.2 divided by 1.2 minus 1 into 288 minus 220. So we are getting 118.3 kilojoules per kg. So net work done per kg of air, that is equal to work done during compression minus work done during expansion. So that is equal to 159 minus 118.3, that is 40.7 kilojoules per kg. So this is the answer. And COP of the plant can be computed like this. We know that the heat absorbed during the constant pressure process 4 to 1 per kg of air is QA T1 minus T4 into 1 into 268 minus 220. So this can be calculated for 48 kilojoules per kg. So COP is equal to, now heat absorbed divided by work done. So that is equal to QA double divided by W. So we get the COP of the plant equal to 1.18. So that is the final answer, students. There ends this problem. we will see a few more problems. It is a little tedious problem. A refrigerating machine of 8 tons capacity working on the Bell-Coleman cycle has an upper limit pressure of 5.2 bar. The pressure and temperature at the start of compression are 1 bar and 16 degree Celsius respectively. The compressed air is cooled at constant pressure to a temperature of 41 degrees Celsius before entering the expansion cylinder. Assuming both expansion and compression process to be isentropic with gamma equal to 1.4, Cp equal to 1.003 kilojoules per kg degree Kelvin. So we have to calculate these 5 parameters: coefficient of performance, quantity of air in circulation per minute, piston displacement of compressor and expander, bore of compressor and expansion cylinders. The unit runs at 240 rpm and is double acting stroke length. So that is equal to 200 millimeters. So power required to drive the unit. So totally we need to find 5 parameters. The given data is Q equal to 6 ton of refrigeration, 6 into 210, that is equal to 1260 kilojoules per minute. So then and there you convert it to our comfortable units. So pressures P2 equal to P3, that is 5.2 bar, P1 equal to P4, that is equal to 1 bar, P1 equal to P4, that is equal to 1 into 10 to the power of 5 Newton per meter square. So these are the pressures, and the temperatures are T1 equal to 16 degrees Celsius, that is equal to 289 degree Kelvin, and T3 equal to 41 degrees Celsius, that is equal to 314 degree Kelvin, and specific heats of air Cp equal to 1.003 kilojoules per kg degree Kelvin. So then we have isentropic index, that is gamma equal to 1.4. So this is the given data. From this we are going to find out those 5 parameters. So this is the cycle PV diagram and TS diagram, and as usual here we know this T1 as well as T3. We need to find T2 as well as T4. So coefficient of performance T2 and T4 be the temperature at the end of compression and expansion respectively. So here the compression and expansion are isentropic. So that is equal to PV power gamma equal to C, and for air gamma is equal to 1.4. So please remember these values, students, 1.4, and using the isentropic relation T2 by T1 equal to P2 by P1 gamma minus 1 divided by gamma equal to 5.2 divided by 1, that is to power 1.4 minus 1 divided by 1.4. So this is the coefficient T2 by T1 ratio, and it is 1.6. So T2 can be find out. T1 into 1.6 equal to 289 into 1.6, that is equal to 462 degree Kelvin. So that is T2. And now T3 divided by T4 equal to P3 by P4. It is during expansion process 3 to 4, and gamma minus 1 divided by gamma, that is the power, and equal to 5.2 to the power 0.286, that comes 1.6, and T4 can be computed from this 1.6 value. So T3 divided by 1.6 equal to 314 divided by 1.6, so that is 196.25 degree Kelvin. So this is the T4, and T2 also we have computed. And now thus the coefficient of performance COP is equal to T4 divided by T3 minus T4. So once we know all the temperatures, we can calculate the COP. It is 1.674. This is the COP. And next is quantity of air in circulation per minute. So let MA, so there is mass of air in circulation in kg per minute. We know that next extracted from the refrigeration machine or refrigerating effect produced per kg of air is QA equal to, in terms of T1 minus T4 into Cp, equal to 1.003 into 289 minus 196.25. So that is 93 kilojoules per kg. Since the refrigerating capacity of the machine is Q equal to 6 tons of refrigeration, that is 6 into 210, that comes 1260 kilojoules per minute. Thus the mass of air in circulation is Ma equal to 1260 divided by 93, that is 13.548 kilojoules per minute. So this is the mass, the quantity of air in circulation per minute. So next is piston displacement of compressor and expander. So let V1 and V4 be the piston displacement per minute of compressor and expander respectively, and characteristic gas constant, that is nothing but R equal to Cp gamma minus 1 divided by gamma, that is equal to 1.003 into 1.4 minus 1 divided by 1.4, that comes 0.287 kilojoules per kg degree Kelvin. So from the ideal gas equation, P1V1 equal to MRT, that is MART1. So then we can find out V1 from the same equation, from ideal gas equation, MART1 divided by P1. So that all values you can substitute here, and V1 can be calculated, that is 11.283 meter cube per minute. So that is the V1. And constant pressure process, during constant pressure process, V4 divided by V1 equal to T4 divided by T1. So we know the V1. So V1 is V1 into T4 divided by T1 equal to V4. So V4 is 7.63 meter cube per minute. So this is the constant during constant pressure process. So next is bore of compressor and expansion cylinders. Let D and D, capital D and small d, be the bore of compressor and expansion cylinders in meters respectively, and the speed of the unit is given, that is 240 rpm, and length of the stroke is given, that is L equal to 200 mm or 0.2 meters. The piston displacement of the compressor cylinder is given by V1 pi by 4 into d square into L into 2 divided by N. So this 2 is nothing but for double acting cylinder. So 240 into 75.4 into d square, solving for d square equal to 0.149. So D equal to 386 millimeters. So this is the D value, and D is nothing but the bore diameter, bore of the compressor. Similarly, for the piston displacement of expansion cylinder is equal to pi by 4 d square into L into 2, that into N equal to 240 into 75.4 into d square. So that is, solving for D, we get 318 millimeters. So expansion cylinder, the bore is equal to 318 millimeters. So power required to drive the unit, we know that the heat absorbed during the constant pressure process 223 is QA equal to MACP into T1 minus T4. So that is substituting all these values is that gives 1260 kilojoules per minute. So that is the QA value. Then the work done per minute is equal to head absorbed divided by COP. So already we have calculated COP 1260, that is the QA, divided by 1.674. So that comes 752.7 kilojoules per minute, students. And the power required to drive the unit is equal to 12.54. So this we are converting into seconds. So kilojoules per second, that is equal to kilowatts. So kilowatt, in terms of kilowatt, it is 12.54 kilowatts. So this is the power required. And the same calculation power required can be done in other way also. This is the alternate method to solve this. The power required to drive the unit may also be calculated using COP. So COP equal to refrigerating capacity of heat absorbed, that is Q divided by work done. 1.674 equal to 6 into 210 divided by work done. So here solving for work done, it is 752.7 kilojoules per minute. So that can be converted into kilojoules per second, that becomes kilowatts. So it is also 12.54 kilowatt. So this is another way to find out the power required. So this is the answer, and we have computed all 5 unknown parameters, and we will see the next problem, students. An air refrigerator works between the pressure limits of 1 bar and 5 bar. The temperature of the air entering the compressor and expansion cylinder are 10 degrees Celsius and 25 degrees Celsius respectively. The expansion and compression flow follow the law PV power 1.3 equal to constant, and we have to find this. The theoretical COP of the refrigerating cycle, the if the load on the refrigerating machine is 10 TR, that is ton of refrigeration, find the amount of air circulated per minute through the system, assuming that the actual COP is 50% of the theoretical COP. So we have to calculate the theoretical COP, and then the half of it is the actual COP. The stroke length and piston diameter of a single acting compressor, if the compressor runs at 300 RPM, and volumetric efficiency is also given 85%. So given data are many data are available here. P1 equal to P4, that is 1 bar. P2 equal to P3, that is 5 bar. T1 equal to 10 degrees Celsius, that becomes 283 Kelvin. T3 equal to 25 degrees Celsius, that becomes 298 degree Kelvin. And polytropic index, that is N equal to 1.3. Cooling load Q equal to 10 ton of refrigeration. So efficiency is actual COP equal to 50% of theoretical COP. Volumetric efficiency is 85%, that is 0.85. And we have compression details. N equal to 300 RPM, stroke length equal to bore ratio L by D equal to 1.5. Specific heats Cp equal to 1.005 kilojoules per kg degree Kelvin. Cv equal to 0.71 kilojoules per kg degree Kelvin. So these are the available data, students. From here, we can find out these 3 tasks. So this is PV diagram, and 283 is the T1 and T3 is 298. And if you see the PV power 1.3 equal to C, it is applicable for both isentropic expansion as well as isentropic compression. So theoretical COP of the refrigerating cycle, let T2 and T4 be the temperatures at the end of compression and expansion respectively, using the isentropic relation of compression, that is 1 to 2 process equal to T2 divided by T1 equal to P2 by P1 into N minus 1 divided by N. So 5 by 1 equal to 1.3 minus 1 divided by 1.3. So this is 1.45 T2 by T1, and T2 equal to T1 into 1.45. We know T1 is equal to 283 degree Kelvin, and that now T2 becomes 410.3 degree Kelvin. So similarly, the expansion process 3 to 4, T3 divided by T4 equal to P3 divided by P4, that is to the power n minus 1 divided by n, that is equal to 1.45. So T4 can be computed from this equation. So that is 205.5. So 205, 5.5 degree Kelvin. and heat extracted from refrigerating system per kg of air. So that is in terms of Cp into T1 minus Ta, that is equal to 1.005 into 283 minus 205.5, that is equal to 78 kilojoules per kg. Work done per kg of air is equal to, it is characteristic gas constant for air is R equal to Cp minus Cv. So that is 1.005 minus 0.071. So that becomes 295 kilojoules per kg degree Kelvin. During work done during compression process is equal to W equal to W1 to 2. So that is equal to N by N minus 1 into R into T2 minus T1. So that is equal to 1.3 divided by 1.3 minus 1 into 0.0295 into 410.3 minus 283, that is equal to 162.7 kilojoules per kg. So that is the heat extracted from the refrigerating system per kg of air. So that is 162.7 kilojoules per kg. Then we can find out the work done during expansion process, that is process 3 to 4, and W equal to W3 minus 4, N divided by N minus 1 into R into T3 minus T4, that is equal to 1.3 divided by 1.3 minus 1 into 0.295 into 298 minus 205.5, that is equal to 118.2 kilojoules per kg. Net work done per kg of air supplied, so that is equal to Wc minus We, 162 minus 118, so that comes 44.5 kilojoules per kg. So theoretical COP of the refrigerating cycle, so that can be calculated by heat extracted divided by work done, that is 78 divided by 44.5, that is equal to 1.75. Amount of air circulated per minute, let MA be the mass of air circulated per minute, and since this actual COP is 50% of the theoretical COP, the actual heat extracted per kg of air is QA equal to 78 into 0.5, that is equal to 39 kilojoules per kg. The refrigerating capacity of the system is Q equal to 10 ton of refrigeration, that is equal to 10 into 210. So 210 is already I have given the table. From there you can take this equal to 2100 kilojoules per minute. So that is given, and from that the mass of air circulated per minute can be calculated. MA equal to 2100 divided by 39, that is equal to 53.8 kg per minute, and this is the answer. And from there we can go and calculate the stroke length and piston diameter of the compressor. Let L equal to stroke length, D is the piston diameter. We have to find this. And since the mass of air supplied to the compressor at point 1 is MA, that is equal to 53.8 kg per minute. So we can calculate its volume using the ideal gas equation. So that is V1 equal to MA RT1 divided by P1. So that comes around 45 meter cube per minute. So substituting all the values, we are getting 45 meter cube per minute, where R I have taken in joules per kg degree Kelvin, and P is in Newton per meter square. So compressor cycle cylinder volume calculation we can do here. We use the formula V1 equal to pi d square by 4 into L into N into volumetric efficiency. So we know the volumetric efficiency also, and 45 equal to D. In terms of D, we are converting this equation, so it comes 300 D cube. So if you solve for D cube equal to 45 divided by 300, that is 0.15. So now D is the 3 D can be computed here, and this is 0.53 meters. In terms of millimeters, it is 530 millimeters. So this is the D value, and we have to find the stroke length also. So stroke length can be computed. L equal to 1.5 into D. So 1.5 into D. So L equal to 1.5 D. So that is equal to 1.5 into 530. That is equal to 795 millimeters. So here the stroke length is 795, the diameter is 530 millimeters. So these are the parameters we need to find from here in this problem, students. We will see a few more problems. So coming to next problem, it is a dense closed cycle refrigeration system and working between 4 bar and 16 bar extracts 126 mg megajoules of heat per hour. So in terms of megajoules, it extracts the heat. The air enters the compressor at 5 degrees Celsius and into the expander at 20 degrees Celsius. Assuming the unit runs at 300 rpm, find power required to run the unit, bore of the compressor, refrigerating capacity in tons of ice at 0 degree Celsius per day. So this is the problem statement. We need to find the pressures. These are the given data. P1 equal to P4 4 bar, and P2 equal to P3 16 bar, and we have refrigerating capacity Q equal to 126 megajoules per hour. So that is equal to 21,000 kilojoules per minute. So temperatures are given. T1 equal to 5 degrees Celsius, 5 plus 273 equal to 270 H, and T3 equal to 20 degrees Celsius, 20 plus 273, 293 degree Kelvin. Compressor details, N equal to 300 RPM, that is the speed, stroke length 300 millimeters, zero point 0.3 meters. Mechanical efficiency is equal to 80 percentage, that is equal to 0.8. Mechanical efficiency of expander equal to, it is 85 percentage, that is equal to 0.85. So this is PV and TS diagrams. So we know T1 and T3, T4 and T2 are unknown, and PV power gamma equal to constant, that is for both isentropic compression and isentropic expansion processes. Then with that available data, we can calculate the power required to run the unit. Let T2 and T4 be the temperatures at the end of compression and expansion respectively. Since the compression and expansion are isentropic, PV power gamma equal to C, and for air gamma equal to 1.4, we use the isentropic relation T2 divided by T1, that is equal to 16 by 4, 1.4 minus 1 by 1.4, that is the power, and 4 to the power 0.286, that is equal to 1.486. So from this we can find T2, so that becomes 413.6 Kelvin. Power required to run the unit. So first one we can calculate. So from previous calculations, you can see here T2 equal to 413 and T4 equal to T3 divided by 1.486 equal to 293 divided by 1.486. So that is equal to 197 Kelvin. So T4 we know now, and also we have calculated T2. So heat extracted from the refrigeration system per kg of air is equal to QA equal to Cp T1 minus T4, that is 1 into 278 minus 197, that is equal to 81 kilojoules per kg. taking Cp of air, that is equal to 1 kg per kg degree Kelvin. So mass of air calculated per minute, MA equal to heat extracted per minute divided by heat extracted per kg of air. So that is equal to 2100 divided by 81 equal to 25.9 kg per minute. So this is one of the answers. And next is work done during the compression process 1 to 2 per kg of air equal to WC is work done from 1 to 2, that is gamma divided by gamma minus 1 into R by NC into T2 minus T1. So substituting all those values, we are getting WC equal to 169.5 kilojoules per kg. Similarly, work done during the expansion process 3 to 4 per kg of air. So WE equal to the similar relation like earlier. So gamma divided by gamma minus 1 into R by NE, that is the efficiency. Then T3 minus T1, T4, that is equal to 1.4 divided by substituting all these values. Then we get 82 kilojoules per kg is the work done for expansion process. So efficiency, expansion efficiency is given, that is 0.85. Net work done per kg of air supplied in the system, WC equal to WC minus WE, so that is 87.5 kilojoules per kg. So power required to run the system is equal to MA into W divided by 60, so that is equal to 37.8 kilowatts. So bore of the diameter, since the mass of air supplied to the compressor at point 1 is MA equal to 25.9 kg per minute, and the volume of air at point 1 is calculated using the ideal gas equation, V1 equal to MA RT1 by P1, that is equal to 25.9 into 287 into 278 divided by 4 into 10 to the power of 5. So that is equal to 5.17 meter cube per minute. So taking R is equal to 287 joules per kg degree Kelvin, and the pressure is in Newton per meter square. So compressor cylinder volume calculations can be done using the formula for piston displacement. So that is V1 equal to pi by 4 d square into L into 2 into N. So substituting those values in terms of D, we get so 141.4 D square. So we can get D square. Then D can be computed, and D square equal to 0.037, and then D equal to square root of 0.037, and this is 0.192 meters. In terms of millimeters, it is 192 millimeters. So refrigerating capacity in tons of ice at 0 degrees Celsius per day. So this can be calculated. We know that the heat extracted or refrigerating capacity of the system per day is Q 126 into 24, that is equal to 3024 megajoules. So that is equal to 3024 into 10 to the power of 3 kilojoules. Since the latent heat of ice is 335 kilojoules per kg, the ice formation capacity of the system per day is 3024 into 10 to the power of 3 divided by 335, and this is 9 tons. This is 9 tons or 9000 kgs. So this is the final refrigerating capacity in terms of tons. So there ends this problem, students. So next example is in an open cycle air refrigeration machine. Air is drawn from a cold chamber at minus 2 degrees Celsius and 1 bar and compressed to 11 bar. It is then cooled at this pressure to a cooler temperature of 20 degrees Celsius and then expanded in the expansion cylinder before being returned to the cold room. So that is the refrigerator room. The compression and expansion are isentropic following PV power 1.4 equal to constant. So for both expansion and compression, the same N and gamma is 1.4. So sketch PV diagrams as well for refrigeration of 50 tons. Find the theoretical COP, rate of circulation of air in kg per minute, piston displacement per minute in the compressor and expander, theoretical power per ton of refrigeration. So this is the given data. T1 is 271 degree Kelvin, T3 is 293 degree Kelvin. So P1 equal to P4, that is equal to 1 into 10 to the power of 5 Newton per meter square. P2 equal to P3, that is equal to 11 bar, that is equal to 11 into 10 to the power of 5 Newton per meter square. Gamma equal to 1.4, Q equal to 15 tonnage of refrigeration, and PV diagram is shown here. And you can see T1 and T3 are known, T4 and T2 is unknown. So we have to find them. So theoretical COP, let T2 and T4 be temperatures at the end of compression and expansion respectively using the isentropic relation of compression 1 to 2. So this can be calculated in terms of P2 by P1, that is gamma minus 1 divided by gamma, that is the power, that is equal to the 271 into 1.985. So that is the T2. So T2 is calculated. So T2 equal to T1 into 1.985 equal to 271 into 1.985, that is equal to 583 degree Kelvin. So that is T2 value, and T4 also can be calculated. T3 divided by T, that is 1.985, that is equal to 293 divided by 1.985, that is equal to 147.6 degree Kelvin. So T2 and T4 also now we have found out. Now we have to calculate the COP. COP in terms of temperatures. So substituting all the temperatures here, 123.4 divided by 121.6, that is equal to 1.015 COP. See, theoretical COP is equal to 1.015. So rate of circulation of air in kg per minute. Refrigeration capacity is 15 ton of refrigeration. Heat extracted per minute, Q equal to 15 into 210. So that is equal to 3150 kilojoules per minute. So heat extracted from cold chamber per kg of air equal to QA Cp T1 minus T4. So that is equal to 123.4 kilojoules per kg. Thus the rate of circulation of air is equal to heat extracted per minute divided by heat extracted per kg of air. So substituting these two, heat extracted per minute, so that is 3150 divided by 123.4, that is equal to 25.5 kg per minute. So that is the one answer. Heat extracted from cold chamber per kg of air is 25.5 kg per minute. And then piston displacement per minute in the compressor and expander. So that is equal to V1 and V2 are the piston displacement per minute in the compressor and expander respectively. V1 equal to MA RT1 by P1, that is equal to, we know all these values, and this is MA already we have found here, 25.5, 287 into 271 divided by 1 into 10 to the power of 5, that is equal to 19.8 meter cube per minute. So that is the piston V1. V1 is piston displacement per minute. And for constant pressure process 4 to 1, V4 by V1 equal to T4 by T1. So from here, we know the V1 value, and substituting that, we can get the V4, that is 10.8 meter cube per minute. And theoretical power per ton of refrigeration, the net work done on the refrigeration machine per unit is work done equal to MA into QR minus QA, that is equal to MA CP T2 minus T3 T1 minus T4. So substituting all the values, we are getting the work done, total work done equal to 3100 kilojoules per minute. The theoretical power of refrigeration machine is 3100 divided by 60, so that is equal to 51.67 kilowatts. And we know that the tonnage is 15, and we are converting that to ton. That is the theoretical power per ton of refrigeration equal to 51.67 divided by 15, that is equal to 3.44 kilowatt per tonnage of refrigeration. So this is the final answer here. Now we have found out all the tasks given in the problem statement, and these are the few problems I wanted to discuss, and a few more problems I will circulate through Google Classroom. I request all the students to practice these problems. Apart from that, I will circulate a few more problems, that is you have to solve and submit through Google Classroom, students. And coming to textbooks, you can refer all these books, and Rajput, C.B. Arora are very good books, textbooks, and also you can have a look into this Kurmi book. It is really a very simple book, and I have taken most of the content from Kurmi book only. You can refer this book, students. We shall stop here. This is. These are the e-resources, and in next class, in next session, we shall start the refrigerants and its nomenclature, classification, and desirable properties. These are the three topics we have to complete in this unit, and that is one session will be sufficient to complete all those three topics. Very simple. We can complete in next session, students. We shall stop here. Thank you, students.